Hello, we will present our final project for the numerical linear algebra course titled Fast Matrix Normalization for Bilinear Pooling using rank-1 update. My name is Andreea Dogaru, and together with Al Suvakitova and Timotei Ardelan, we form the A-STAR team. We begin by introducing the background of our project. Then we briefly present the theoretical framework on which the solution is built. We continue with the obtained results, and in the end, we summarize our findings. Fine-grained visual recognition is a computer vision task more challenging than generic object recognition because the intra-category differences are small and can be overwhelmed by factors like pose, visualization perspective, or localization of the object in the image. For example, some bird species are differentiated only by their beak pattern. Motivated by the past developments in handcrafted features, the bilinear convolutional neural networks, which integrate second-order pooling strategies, have been proposed. These models essentially employ covariance descriptors within CNNs, benefiting from higher-order statistics of local features inside each image region. The output of second-order pooling is a bilinear matrix that is used to make the classification. However, reference works have shown that we need to normalize these matrices' singular values to achieve high performance. Previous normalization methods that have been used are based on singular value decomposition and Newton-Schulz iteration. These methods have various disadvantages like bad compatibility with GPU platforms and require costly computations. A drawback of bilinear CNNs is that when the bilinear matrix is vectorized before the classification layer, we obtain a very large vector, which makes these networks memory-intensive and subject to overfitting. A solution to this limitation is compact bilinear pooling, which approximates the feature map. Two such methods are TensorSketch and random McLaurin, which can reduce the dimensionality by 2 orders of magnitude with very little loss in performance. Because compact bilinear pooling shows a significant improvement, the matrix normalization method should be compatible with such compact features.
And here's the problem statement for our project. Our goal is to implement and test run algorithm for bilinear matrix normalization. It was proposed in paper called Towards Faster and Simpler Matrix Normalization by rank-1 update by Yu et al. Unlike its predecessors, run is based on iterations of matrix by vector multiplications, which are computationally cheaper than the matrix by matrix multiplications. The algorithm supports normalization on compact bilinear pooling features. Moreover, run is differentiable, which means that it can be plugged into a neural network for an end-to-end training. Here you can see the exact algorithm for run. As you can see, it is based on standard power iteration method. As an input, it takes feature map and two hyperparameters, and the output will be normalized feature map. It is initialized with random vector. The algorithm consists of only two matrix by vector multiplications per iteration. Therefore, its complexity is O of kdn. All previous approaches had complexity of O of d cubed. But because depth is much bigger than width, height, or number of iterations, run gains a significant speedup. Moreover, since the algorithm is applied directly on the feature map, it is compatible with compact bilinear pooling. And now about our experimentation. On this slide you can see the architecture of the implemented convolutional neural network. As a backbone, we use pre-trained VGG16. Run denotes the proposed rank-1 update normalization, which takes as an input the feature map of the last convolutional layer. BP denotes the bilinear pooling and CBP represents compact bilinear pooling. The obtained BP-CBP feature is fed into the softmax classifier. We conduct experiments on three tasks: fine-grained recognition, scene recognition, and texture recognition. On the fine-grained recognition task, experiments are conducted on CUB dataset. On the scene recognition task, experiments are conducted on MIT dataset. On the texture recognition task, we test our method on DDT. The thing that unifies these datasets is that distinguishing between objects in them often implies focusing on details from coarser to finer levels, such as the beak of a bird for example, because this works as a discriminating feature for recognition.
Considering results, we first and foremost present the accuracy of the implemented method. We compare the result with two baselines, BCNN and improved BCNN. The former uses bilinear pooling followed by sine square root and L2 normalization. This relatively simple method obtains significantly better results compared to using average or max pooling, for example. The second baseline, improved BCNN, in addition to the normalization steps performed by the first method, computes the matrix square root of the bilinear matrix. The benefits of this additional step is about 1 to 2% increase in accuracy. However, to compute a matrix square root is inefficient on GPU if calculated by using the SVD decomposition. The proposed alternative is to use Newton-Schulz iterations. However, this variant is still quite time-consuming. In run, this normalization step is replaced by the rank-1 update normalization, which can be computed efficiently using just matrix by vector products. It surpasses the simple BCNN on all three datasets and even performs better than improved BCNN in two of them. Moreover, the benefits are visible when comparing execution time. Run obtains about 10-fold increase in speed compared to IBCNN. It is only marginally slower than BCNN while offering an important increase in accuracy. The time presented here is expressed in milliseconds, and it strictly captures the part of the network referring to computing the bilinear features. To summarize our findings, we managed to reproduce the results leading to and including the development of run. We showed that proper normalization of the bilinear matrix proved to be indeed important in the fine-grained visual recognition task. We observed that run is significantly faster than IBCNN, while leading to similar or even superior accuracy. An important finding is that run works better with uniform distribution initialization compared to normal distribution used in the paper for initializing the vector for power method. This small-looking change proved to play an important role in obtaining stable training and a well-performing network. In conclusion, we investigated BCNN and various matrix normalization approaches. We implemented run algorithm as well as the setup needed for training, evaluating, and benchmarking the neural networks. We reproduced the most important results of the paper and confirmed the benefits of the proposed method. Thank you for your attention. We are now ready to answer your questions.